on this computer. Cool. Okay, so we are getting very close to the end of the course now. This is the 13th lecture set, which is our last lecture set for Stat 252. And you can see that the topic of this is multiple linear regression. So this would be the general case of what we studied in lecture set 12. So just as a reminder, lecture set 12 was simple linear regression. And that's about half of assignment number 6, which is also the last assignment for the course. The other portion of that assignment will be the first sort of half for the first, let's say, 1/3 of lecture set 13, which is the one that we are currently on. So we'll start to dive into the material you need for the MLR parts of assignment number 6 today. Just a few notes. So there was two major topics that we studied in the Friday lecture. That was the asynchronous lecture. And those were the conditional mean interval and the prediction interval. Now, those were the only two inferential procedures that you likely have not seen before. The other inferential procedure that we studied in the asynchronous lecture was the hypothesis test about beta 1 and the corresponding confidence interval about beta 1. Okay, so these two procedures, which come right at the end of the lecture set, those will likely be the two procedures that you haven't seen before. Now, the other thing to consider is that these are very similar in their structure. There's only a very small difference between them. And in the lecture set, I discussed why we interpret them differently and also what you can expect in terms of the construction of the interval when you use the conditional mean versus prediction. Okay, so before I get into the new stuff, does anyone have any questions about that material that I did cover on Friday? Oh, and note that those two, these two intervals are on assignment number 6. So there is at least one question. I think there's one question for each of them on the 6 assignments. All right, not seeing any, but as always, if something comes up, don't hesitate to ask. Okay. All right, so this is a longer lecture set. So we actually cover a lot of different topics in this lecture set. The first sort of, let's say from here to here, this would be the most important part of the lecture set. So sort of the foundational aspects of our study of multiple linear regression. And then we have three other topics, which are shown here. So this would be, let's say like extension 1, extension 2, and extension 3. Okay, so we're gonna focus on getting through the foundational stuff. We have today, tomorrow, Friday, you have a quiz, and then next week. So we have about 5 lectures to try and make our way through all of this. So we'll get as far as we can. The foundational stuff, of course, is the most important. I think we'll definitely get through the dummy variable aspect as well. So the categorical variable inclusion in the MLR, that's also a very good unit. Model selection, if we don't get to it, it's not really a big deal. And the kth order stuff can be useful as well, but really it's that foundational stuff in the first extension that I would really like to get done before the end of the semester. And the other two, I would just consider a bonus if we do get there. All right, what is the multiple linear regression model? So the multiple linear regression model is a direct extension of the simple linear regression model. The simple linear regression model, actually, it's better put this way, is a special case of the MLR model. So SLR occurs when K is equal to 1. So you can see in equation 1, we have yi, which is the response variable, is equal to beta 0. Beta 0 is what we call the intercept, same definition as before. So it's just a constant, it's just some number, plus, and then we have beta 1 x1I up to beta k xik. So in the MLR model, we are considering k explanatory variables. So the assumption is essentially that our response variable, the yi, forms a linear relationship with each explanatory variable. So yi is linear with x1, yi is linear with x2, yi is linear with x3, yi is linear with ... xk. Okay, and there's no real boundary on what k can be equal to. I mean, typically you wouldn't observe k greater than n, and ideally k is as small as possible. So we only want to use the most informative explanatory variables when we're using multiple linear regression. Each explanatory variable, so each x, has its own slope, and the slope has the same definition that it had in the simple linear regression case. So the slope is basically just a value that tells us how the response variable changes with a unit increase in x. We have to make a condition in this case, and we'll talk about that in a little bit because we have so many explanatory values, but it's the same underlying principle. And then finally, you can see that we also tag on the error term, and the error term is defined in the exact same way that it was in the SLR case, because again, SLR is just a special case of MLR when k is equal to 1. When we studied simple linear regression in lecture set 12, we showed that B0 is equal to y bar minus B1 x bar, and B1 is equal to SXY over SXX. Excuse me. Now, in the multiple linear regression case, deriving the estimates for each of the slope terms is done in the exact same way. So we're trying to minimize that sum of the squared error term, or use the least squares approach, just like we talked about in SLR. The problem is that every time you add an explanatory value into the system, the formulas for each of the slope terms becomes more complicated because you have to include that additional information in the estimate. So for the purpose of this class, we're not going to talk about the general solution to the MLR system because that requires an understanding of linear algebra and being able to essentially work with matrices. And that's beyond the scope of what we're trying to do here. In this course, we're focused on the same things that we were, or in this course, we're focused on inference and utilizing the fitted model. So that's going to be our focus. So while you can solve for each of the beta j directly, that solution is, again, requires techniques that are beyond the scope of what we have studied here. Okay, so to illustrate an MLR model, we're going to start with a fairly simple idea, or a fairly simple data set. So in this data set, what we are measuring is the taste score for one of 30 different cheeses. And we are trying to model the taste score as a function of the acidity, the amount of dihydrogen sulfide, and the amount of lactose in each of the cheeses. Okay, so we have our response variable, which is the y. We have the acidity, which we can call x1, H2S, which we can call x2, and the lactic value, which we can call x3. When we are studying or when we are working with MLR, you can see that each observation, so this, for example, is observation 1, contains multiple measurements. So observation 1 here has 4 different variables associated with it: taste, acidic, H2S, and lactate, right? Observation 2 is the same idea. So it also has 4 different measurements associated with it: taste, acidic, H2S, and lactate. So the observations are now a collection of different variables, or each observation is now a collection of 4 variables in this particular case. So we have P is equal to 4 variables. K is equal to 3 explanatory variables. And as always, we have one response. Now, the assumption that we are making here is that we can fit. So we assume that yi is equal to beta 0 plus beta 1 x1i. Is that how I read it before? x1i, yep. Plus beta 2 x2i plus beta 3 x3i plus the epsilon I. So we are assuming that the response variable and each explanatory variable have a linear relationship. So that would be the same as the first assumption that we used in the SLR case. In fact, the 4 assumptions that we used for SLR are exactly the same as the assumptions that we're using here, because again, SLR is a special case of MLR, or simple linear regression is a special case of multiple linear regression. So the first assumption is linearity between the response and the explanatory variable. All right, on slide 5, we have what is called a scatterplot matrix, or like a pairwise scatterplot. And this is something that we can produce in SPSS directly, and that's what we'll learn how to do in the lab at the end of this week. So the way that we read the scatterplot depends on the plot that you are looking at. So in the first row here, okay, so this would be row 1. Each of the 3 plots show taste on the y-axis. Okay, so row 1 shows taste on y-axis. So that's the natural position for the taste variable, because that is the response variable for our problem. Now in column 2, which is shown here, we have acidic on the x-axis. So that means that the first scatter plot here, this scatter plot is taste versus acidic. Okay, so this is the same thing as the general or the individual scatter plot for taste versus acidic. That means that this plot here is taste versus H2S. So you can see that from the scatter plot matrix, if we go to row 1, column 3, that's where H2S is on the x-axis. And then if we go to the last scatter plot, which is shown here, we have taste versus lactic. So in order to determine if our response variable forms a linear relationship with each explanatory variable, we can use or focus on the first row of the data set. So we can focus on row 1. Now that being said, you can gain a lot of additional information from looking at the other plots in the scatter plot matrix. For example, here, okay, we have acidic versus H2S, right? So this is showing us a scatter plot of x1 versus x2. Here we have acidic versus lactic. So that's showing us a scatter plot of the acidic variable versus the lactic variable. Studying the relationship between the explanatory values can be very helpful to us, because ideally we're not going to see any relationship. So this can show us if it appears random. The reasons why we would want that is something we would discuss in the 3rd year class on regression. But the point is simply that the scatter plot matrix gives us the ability to study the relationships between not only the response variables and the explanatory variables, but also between the explanatory variables compared to one another. Okay, so in the first row, we have taste versus each of these variables. What we want to basically do is use the scatter plots the same way that we did before. So we want to determine if, or we want to use the scatter plots to determine if there's evidence of a linear relationship between the response variable and each explanatory value. So if we were to take these first 3 plots and just sort of draw a straight line through the middle of each plot. So maybe here, here, something like that. What we can see from the plot, so we'll call this 1, 2, 3. Okay, so what we can see from the plot is taste versus acidic does not appear to have a strong linear relationship. Is this thing going to cut out on me? I might get disconnected here momentarily. We'll see. Okay, and you can see that that's true because the points are deviating quite far from the line, and also it just kind of it does look like there's a positive relationship, but appears quite random. For the second plot, compared to the first one, this definitely appears to be a much better fit. So this relationship looks more linear. You can see a better bound in terms of the variance around the line. So the points appear to be fairly well spread, but they are at least increasing in a linear fashion. So taste versus H2S does appear to form a linear relationship. And then 3, I would argue is the same conclusion as with the second plot. So the points appear to be a little bit more spread away from the line, but in general, the relationship does look to be linear because you see that kind of constant bound across the variance around those points. Okay, so taste versus lactic is also linear. And again, the purpose of this exercise is really just verification of that first model of the first assumption, which is a linear relationship between each response and the predictors. Okay, does anyone have any questions so far? All right, so the table shown below is giving us information about the fitted line. So you can see that we have a coefficient row, we have a t-value row, and we have a p-value row. So each of these coefficients represents one of the model parameters. The t-value and the p-value represent individual tests about the coefficient. Okay, so let's highlight these values here. So what each of these rows is showing us is a test about the intercept term being equal to 0 versus the two-sided alternative. So this would be beta 1 equals 0. This would be beta 2 equals 0. And this would be beta 3 equals to 0. Right? Okay, so this information here is effectively for the test of no relationship between each of the different explanatory variables and the response variable for the model. Okay, and that would actually just fall into these 3 categories here. So these are tests of no linear relationship. Now, as we will see when we progress through the lecture material, because the system includes additional explanatory variables, we have to incorporate that into not only the interpretation of the model, but into how we validate the model. So while these tests can be useful as individual tests, they are conditional tests in the sense that you are testing that beta 1 is equal to 0, given that the other values still are in the model. Okay, so all tests of linear relationship are conducted assuming other variables are still in the model. Now, this idea also holds true for the interpretation. So let's take a look at examples of how that would work. First, if we wanted to actually utilize the information above, we would have the following. Okay, so from output, we have yi is equal to b0 plus b1 x1i plus b2 x2i plus b3 x3i. Okay, so this is going to be negative 28.8768 plus 0.3277 x1i plus 3.9118 x2i plus 19.6705 x3i. Okay, so the output is showing us the equation of the fitted line. All right, so for beta 0, we have the following. When x1, or sorry, let's interpret it in terms of the actual problems. So when the acidic H2S and lactic values equal 0, the expected taste score is negative 28.8768. Okay, so first, beta 0. Beta 0 is the y-intercept for the model. So this is the expected value of the response when all of the explanatory values equal 0. So the definition is exactly the same as we saw in the simple linear regression case. In this case, we have three explanatory variables, acidic, H2S, and lactic. So what beta 0 is telling us is what we expect the taste score to equal when each of those three values are equal to 0. Okay. Now, one thing to keep in mind here in terms of a practical solution is that this probably doesn't make any sense. So the interpretation of B0 is likely meaningless since a score of negative 28.88 is likely impossible. Okay, so I can't say for sure if the scoring system uses kind of a standard set of values. So you would assume that the scores for each of the cheeses have to be between like 0 and 100, say. But my guess is that a score of negative 28 is probably impossible because they wouldn't score a cheese in terms of taste below a value of 0. So more than likely, this interpretation is not actually meaningful to us in the context of what the problem is actually saying. So it's basically telling us like if any of these three values are equal to 0, which probably wouldn't even form a normal cheese anyways, because if the cheese doesn't have any acidity, no H2S, and no lactic value, it's probably not even a cheese. It's most likely the case that would just get a score of 0 or not even exist. So for multiple reasons, this probably doesn't actually make or have any meaningful any actual meaning in terms of the problem. All right. For beta 1, we are interpreting the value of acidic. So what we would do here is, given the H2S and lactic values are held constant, we expect the taste score to increase by 0.3277 units for every 1 unit increase in acidic. Okay. So this interpretation is pretty much exactly the same as what we saw before as well. We're basically just saying how we expect the response variable to change with each unit increase in the explanatory variable of interest. So if the acidic value increases by 1 unit, we expect the taste score to increase by 0.3277, but only if x2 and x3 are held constant. So again, what you can see here is that in the MLR case, a lot of the initial ways of working with the model are the same. But the big difference is that when we interpret the model or use those tests of no relationship, those are conditional on the other values either being held constant or remaining in the model. Okay, so for beta 1, or for beta 2 rather, we would have a very similar interpretation. The only difference here is that we're now conditioning on acidic and lactic. Okay, so here we would have, given acidic and lactic values are held constant, we expect the taste score to increase by 3.9118 units for every 1 unit increase in H2S. Okay, and then for beta 3, we would again have the same idea, but now we would be conditioning on H2S and acidic. So we would have, given the H2S and acidic values are held constant, we would expect the taste score to increase by 19.6705 units for every 1 unit increase in lactic. Okay, does anyone have any questions? Okay. All right, so we have the general model we have the general formula for an MLR model. We have basically discussed that the first assumption is exactly the same, except we just extended across all response explanatory comparisons. Now we have talked about how we would interpret each of the different values, which is basically the same as in the SLR case, except you condition on the other values being held constant. The next thing that we would be interested then in doing is evaluating the model. Okay, so we fit this MLR model. Is it any good? Or is it useful to us? So one of the ways that we can evaluate that question is by using a diagnostic measure like the coefficient of determination. Now, for an MLR model, the coefficient of determination has the exact same definition that it had in the SLR case. So it's R squared is equal to SSR over SST, or 1 minus SSE over SST. So for the data set that we're working with, the R squared here would be which is equal to 1 minus 2,668.41 divided by 7,662.89, which is equal to 0.6518. Okay, so therefore, the fitted regression line explains 65.18% of the variation in the response variable. Right, so it's the same interpretation and the same calculation for the R squared value. Now, there's a drawback to using this approach. If we use the R squared as it was defined above, this value will always increase as we add predictors into the model. Okay, so every time we add a new explanatory value into the model, the R squared is going to go up. And the idea here is that if K is equal to N, so basically you give each observation or each explanatory value, or you give, sorry, if you give each observation its own explanatory value, you're going to be able to account for all of the information in the response variable using the line. But the problem is you're going to drastically overcomplicate the model. Okay, even though we can include multiple explanatory variables, we don't necessarily want to. We still want to have the simplest possible system that we can so that we can make the most direct conclusions that we can. For example, saying that taste score changes by 19 units with a 1 unit increase in lactic, given that H2S and acidic are constant, that has some meaning to us. The general person can understand what that is effectively implying. But if you have 30 explanatory values and you say that the taste score is going to increase by this many units if it's for a 1 unit increase in acidic, given that the other 29 are held constant, that's a very complicated system, and it can be more difficult to understand exactly what's driving the change in the response. So using the R squared as a tool to evaluate an MLR model does not give the same benefits as it does in the SLR case when you're constrained to only using one explanatory value for each model. Furthermore, if say you fitted 2 MLR models, okay, so suppose you have y equals beta 0 plus beta 1 x1 plus beta 2 x2, and y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Okay, and you wanted to compare those two models for the same data set. The second model with 3 explanatory values is always going to return a higher R squared. So even if the simpler model is actually the better model based off of all other criteria, the R squared is always going to suggest the bigger model is the better model. So in order to adjust the R squared to be useful to us in the context of an MLR problem, we use what is called the adjusted R squared. And the adjusted R squared, instead of taking SSE over SST, takes MSE over MST. where MSE is the SSE divided by n minus k minus 1, and MST is the SST divided by n minus 1. Now, the purpose of this measurement is to be able to allow us to fairly compare different MLR models for the same data set. So for example, for the cheese data set, if we have a simple model based off of only 2 variables and a more complicated model based off of 3 variables, the adjusted R-squared is going to allow us to compare those models in a more fair way. So to illustrate that, consider again the output for that cheese illustration that we were talking about before. So in problem 1, we want to find the adjusted R-squared value. All right. Now, before we do this, let me just show you a few things about how this value would come about. So we know for any MLR model that we can decompose the total sum of square into a sum of square regression term and a sum of square error term. That means that we can construct an ANOVA table to represent the problem that we are working on. Okay, so we have DF, SS, MS, and then there would also be an F statistic, for example. Okay, so the total degree of freedom is the number of observations in the data set minus 1. So that would be 29. This degrees of freedom for the regression term is the number of observations minus k minus 1. So in this case, it would be 30 minus 3 minus 1, right? So that's going to be, or no, sorry, that's the error term. The DF regression is going to be the number of slope terms. So it's actually just equal to k. So this is going to be 3. Okay. And then the error is going to be the difference, which is 26. Okay, from the previous illustration here, we were given SST, which is 7,662.89. And we were given SSE, which was 2,668.41. So both of those values came from the previous illustration. Right. Okay, so we can find the SS regression by taking 7,662.89 and subtracting 2,668.41. So that gives us 4,994.48. Right. Then we can easily get each of the mean square terms just by dividing the sum of square by the degree of freedom. Okay, so for example, the SSR or the MSR is going to be 4,994.48 over 3. Okay, and then our MSE is going to be 2,668.41 over 26, which is 102.6312. And then we can also compute the F value. We'll come back to talk about this a little bit later, but that would be found just by taking the ratio of the two mean squares. And that gives us 16.22145. Right. So the purpose of this little description of the ANOVA table is just to show you how we can summarize the information for an MLR model. And also to show you that this concept that we learned about ANOVA earlier on, it can still be applied in the MLR case. And actually that those earlier ANOVA models that we studied are really special cases of these multiple linear regression models. All right. So we wanted to compute the adjusted R squared. So we have R squared E is 1 minus MSE over MST. That's 1 minus 10 2.6312 divided by 1. Oh, MST. So that's going to be, actually, we need that one too. So 7,662.89 divided by 29. So that's 264.2376. So 264.2376. And that gives us 0.6116. Okay, so this is the adjusted R-squared for the full model. Now again, the purpose of introducing the adjusted R-squared is to give us an evaluation of the model that would be more fair if we considered other MLR models for the same data set. So in exercise number 2, it says, if we wanted to reduce the number of predictors here, what could we do? All right, well, we could say remove the acidic variable since the p-value equals 0.942 for the test H0 beta 1 equals 0 versus HA beta 1 not equal to 0 given H2S and lactic are in the model. Okay, so the output above here is showing us that there's no evidence that the acidic variable and the response variable form a linear relationship. So we have no evidence to reject the null hypothesis that beta 1 is equal to 0 given H2S and lactic are actually in the model. So if we remove the acidic variable, then we now have, in terms of the values we've been using before, okay, we now have the following model. So suppose that for this model, the SSE is equal to 2,668.97. Okay, so now what we have is a ANOVA table for the model in exercise number 2 that's going to look like this. So we'll have 29 degree of freedom again, but now we only have 2 DF for the regression term because there's only 2 explanatory values in this reduced model. So that gives us an additional degree of freedom for the error term. Okay, now the total DF, or the total sum of square, is going to be exactly the same. Okay. Therefore, the total mean square is also going to be exactly the same. But we have one less regression term. So the error term here, you can see, has increased to 2,668.97, albeit it's a very small increase, which means that we have an SS regression of okay. And now, if we wanted to find each of the MS terms, we would have, using the usual properties of the ANOVA table, so SS over DF okay. Right, so you can kind of see where this is going. We have a smaller mean squared error. So the adjusted R squared here is now going to be, for the reduced model, 1 minus 98.85074 divided by 264.2376, which is equal to 0.6259. Okay, so that implies that the reduced model, so by removing a variable, we actually improve our fit. So the adjusted R-squared is higher for the reduced model than it is for the full model, which means that this reduced model is providing a better fit or explains more of the variation in the response than the full model does. So we can gain information by taking the acidic variable out of the problem. Okay, so question 4 is just asking us to summarize that idea. So we can say, since the RA squared for the reduced model is larger than that of the full model, the reduced model is a better fit for this data set. Okay, now, with that being said, when we are comparing the adjusted R-squared values, this isn't a formal hypothesis test. So we're just comparing two numbers to one another and we're saying this one is higher, which implies that this model is better. But what we have learned throughout the course is that when we want to make these kind of comparisons or state with any kind of certainty or any sort of evidence that one thing or one model is better than another or one approach is better than another, we need to be able to compare those using a statistical hypothesis test. So the next thing that we're going to learn how to do is take the information from these ANOVA tables and turn that into a test about how useful the model really is. So in the simple linear regression case, we had the test or the model utility test or the test of no linear relationship, which was that t-test that we talked about in lecture set number 12. And in that t-test, we had H0 beta 1 equals 0 versus HA beta 1 different from 0. For this MLR model, you notice that we have a t-test for each of the different slope parameters. But what we require is a general test about how useful the model is as a whole. So the next thing that we're going to study is this test for all of this, for the entire system at once. So we're going to construct a general model utility test for the entire multiple linear regression model. And this utility test is actually going to be run using the output from the ANOVA table that we showed in exercise number 1. So for each model, we can build an ANOVA table, we can find an F value, and that F value effectively is the F value testing whether or not all of the slopes are equal to 0 versus the alternative that at least one slope is different from 0. Okay, so that's what we will start with on Wednesday. And as always, if you guys have any questions, please let me know. And otherwise, I'll speak to you on Wednesday afternoon.